This video showcases a machine learning-based prototype system developed for the detection of RF anomalies. Although the system is a project in work, it seems to show promise for this application area. Our hope with this video is to engage with interested customers and companies in some partnering sense to allow continued development and potential fielding of a robust system for detection of RF anomalies. In this video, we'll first go through a brief overview of the RF anomaly detection problem. Next, we'll take a look at the current work related to the project. Then we will follow this with some demonstration of the current system, followed by some ideas for potential partnering. So, an RF anomaly. What exactly is that? Well, an RF anomaly is some kind of RF energy in a band of interest which differs from the normal ambient RF energy in that band, or what you might consider the baseline RF energy. This RF baseline includes all the RF energy from background RF, as well as any intended or unintended signals from equipment normally operating in that RF band of interest. Another way of thinking about it is that an anomaly is typically considered something which deviates from the norm. So, anomaly detection, what is that? Well, basically we want to identify some type of unexpected signal in the RF spectrum. For example, if we look at this demonstration, we've got some ambient energy here, looking at a spectrogram of some signal, and all of a sudden we see a new signal show up. In this case, it's a swept sine wave. In our example here, we would interpret this as being the anomaly. We'll take a different look at this from a waterfall perspective, and you can see the anomaly, the anomalous swept sine wave moving within our normal ambient energy, and now it went away. So the idea is that we want to be able to detect that that occurred. What is the inherent difficulty in RF anomaly detection? Well, basically the determination of what exactly is normal and what exactly is an anomaly. This is made more difficult as anomalies by their very nature are not defined as a single specific type of known RF energy, and therefore cannot be considered in any type of a priori sense when developing an algorithm for the detection of them. This is a one-class type of problem, where we only have samples of good or normal RF energy to study and train on. Everything else, whatever that is assumed to be bad or an anomaly. Why should we work on this problem? What are the reasons to explore this? Well, first, it is a technically interesting and challenging problem, and one with possible real-world applications which also allows us to utilize their expertise and resources in machine learning and signal processing. Secondly, if this problem can be solved, it has direct potential to help in areas of increasing importance to our country. Finally, there is a real potential to generate revenue for the companies that produce a good solution to this problem. At this point, we have developed a basic proof of concept prototype system. It is a PC-based Ubuntu application which uses a COTS SDR for the RF acquisition. The system uses a machine learning-based algorithm in the back end with DSP-based feature extraction on the front end. This could be considered a phase 1 type of R&D. There are still unknowns and issues to address. However, having said that, the system does seem to show some promise in some areas. To date, we have committed about $250K of NRE towards the R&D of the current system. A good question might be, what's left to do? Well, again, this is a phase 1 effort, so there is more work to do, namely in improving the system in areas of detection, more formal testing and characterization, and so forth. In addition, potentially there could be application-specific design aspects that might be considered and addressed, as well as possible integration with other systems, perhaps other SDR RF acquisition hardware, or even file-based types of RF input. Eventually, basic productization, documentation, and other types of things may need to be addressed as well. This is an actual screen capture of the anomaly detection system. In the middle of the application, you can see a live running spectrogram showing the RF energy versus time. On the upper portion, there are multiple displays showing a variety of internal extracted features. The lower left area is for the machine learning control, while the lower right area is used for the anomaly detection displays. Note that the anomaly detection display shows the current T0 detection status, along with 7 prior historical detections, T1 through T7. Now a little bit about the nature of the RF acquisition of the system. Currently, while the system is running, RFIQ samples are acquired using non-real-time buffering. The nature of this buffering is to grab a half-second of real-time RF signal and subsequently process that data, which takes about 4 seconds to complete. The system continually repeats this acquiring processing process, which effectively allows it to operate on a sampled basis of about a half-second of RF signal analyzed every 4 seconds. The RF is actually being captured when the red indicator is on. The RF is then being processed when the red capture indicator is off. With further work, the real-time nature could possibly be improved, if this is even necessary. We'll next briefly discuss some aspects of the machine learning system, namely training the machine learning system. When the system starts up, the machine learning system is not loaded, so either the user would load an existing weight file or begin a training session to create a new weight file. Note that when there is no weight file loaded, the anomaly detection displays are disabled. After initiating machine learning training, a blue indicator will show the training progress while the system is being trained. After completing training, typically about 5 to 10 minutes currently, the blue indicator will complete and the anomaly detection displays will be enabled as the system automatically starts to look for anomalies in the RF. And now for some demonstrations of the anomaly detection system. First, some demonstration details. In these demonstrations, we are using a USRP SDR with either 5 or 10 MHz bandwidth with an acquisition size of a half a second. For demos with LTE signals, we are using radiated or over-the-air live input with a cell a few miles away. For demos with CDMA signals, we are using a base station emulator as the input to the system. The anomalies are generated by a Rodian-Schwarz signal generator, and the anomalies are added in conductive mode using a Rodian-Schwarz RF combiner. Although for these demos we are using communication system signals as the primary energy for the ambient RF energy in the spectrum, note that there is nothing specific in the system related to what type of RF energy constitutes the ambient RF energy. With regard to the demonstration method, there are 3 simple steps in each demo. Step 1 is to monitor the ambient RF spectrum with no anomalies. Step 2 is to turn on or add an anomaly to the RF environment and observe what happens. Step 3 is to turn off or remove the anomaly from the RF environment and observe what happens. Note, the system has been prior trained for each demo example. The first 2 demos each include an LTE signal with an anomalous tone added within the band. In the second demo, the anomalous tone is at a much reduced signal level. There are 4 additional demos located after the contact information at the end of the video. In demo 1, we're looking at an LTE channel with an anomalous tone added within the channel. So here's an LTE signal from about 4 miles away. We can see the spectrogram running in the middle. Now we're going to turn on an anomalous tone. There it is. And we'll watch in the lower right as the anomaly detection happens. You can see that that tone is being seen quite easily by the system, and the detection is shown up quite obviously in the lower right. Now the tone is removed, and again we'll watch what happens in the lower right detection display. Note that there's no detection of an anomaly at this point. Now in this example, that tone was actually at a pretty heavy level within the channel. Demo 2, we're going to add a weaker anomalous tone within the channel. So again, we're running as before with an LTE signal. And now we've added a tone. You can see it's much reduced from the prior example. And in lower right, you notice we are detecting it, although it's not maxed out as it was in the prior example. So as we're running along, we're still detecting it. Again, it's a weaker tone. It's buried within the channel. Notice that it's actually lower than some of the other energy within the channel. And here we actually missed it. That was a mistake on the system. And that's again because the tone was so low. Now that the tone's been removed and we are again not detecting as we should be. So in this example you can see one mistake the system made. But again, that tone is fairly low level and it is buried within the channel. With regard to partnering possibilities, for those companies engaged in related business, their areas of interest might include accelerating potential customer contract wins in the RF spectrum management area. Additionally, partnering may help the company with future product positioning or product sales. Potentially working together may enhance existing development and product areas synergistically. In this case, some possible partnering ideas might include direct NRE funding of continued development, purchase of the existing design of the prototype system, or some type of resale royalty arrangement. For direct customers with potential interest in this area, they may have a goal to create a robust system for RF anomaly detection. They may wish to advance our technical capabilities in this important area. They might want to discover potential issues or roadblocks in this area, along with possible solutions. In this case, some partnering ideas might include funding of some type of study in this area, direct NRE funding of continued system development, or purchase of initial test beds and/or prototype systems. Of course, these are simply some ideas for possible partnering. We are open to other ideas as well.